Hi, Doc Revis here. In this video, I'll show you how to draw Lewis structures for compounds that have multiple bonds. We recommend our other video on single bonds that go into more detail on the basic principles. First, we begin by considering the periodic table, which shows us the valence electrons that are involved in drawing Lewis dot structures. Valence electrons combine to fit the octet rule of 8 or other stable configurations based upon the element's position on the periodic table. Let's show you how to draw these Lewis structures of multiple bonds by starting with an example, hydrogen cyanide, as shown here. If you consider the Lewis structures or Lewis dots around each of the individual elements, they will look like that shown on this slide, where hydrogen has 1 electron, carbon has 4 electrons, and nitrogen has 5 electrons, of which 2 form a lone pair. Following the rules that were taught for drawing single bonds, we first lay out the Lewis structures of the individual elements as shown here, with carbon being the central atom since it's in group 14 or 4A, and then we have hydrogen and nitrogen will form the peripheral or the perimeter elements. So step 1 is draw the valence electrons around, assuming 4 sides of the elements. Step 2, we extend a short line or bond from each dot simply to show the overlap of where the orbitals will be. Keep in mind, this is simply to show where the overlaps will occur. The third thing we do is to attach each of the elements to the central atom. So we first place carbon and then hydrogen, and we follow that with nitrogen by attaching them to the individual bonds. Note that carbon has 4 lines extended from it, which suggests that it has the potential to form at least 4 bonds. Now that we've drawn this basic skeleton, we now start to pair the electrons. We pair the electrons by erasing the lines and shifting the dots to the middle of the structure. Keep in mind, in a Lewis structure, you want to make sure that all the electrons are paired. Never leave an unpaired electron when drawing a Lewis structure. If we do that, we create a structure as shown here, and now we count the electrons around each of the elements to determine whether or not we have a sufficient octet rule. And if we look at that, we discover that we have 8 electrons around carbon, 8 electrons around nitrogen, and that fulfills the octet rule. If we examine hydrogen, we notice there are 2 electrons, and that satisfies its need for electronic balance. When we consider Lewis structures, we note that elements in the same group, that is, the same columns, will form similar Lewis structures, and we show you an example here of hydrogen cyanide and the other elements in group 14 and the elements in group 15, and they will form similar Lewis structures as those shown here. Let's try another example, carbon dioxide. Again, we show you the periodic table for valence electrons. If we draw out the Lewis dots around each of the elements, it will look like so, where carbon is the central atom and oxygen will be on the peripheral. We follow each of our steps, draw the electron dots, assuming 4 sides. If we do that in the case of oxygen, we note that we will have 2 sets of lone pair electrons. These will be the electrons that will not participate initially in bonding. Step 2, we extend lines or bonds from these simply to show where the potential bonds might be formed. Again, these lines are drawn to show where the orbitals will overlap for the initial bonds. And then we draw carbon as our central atom and proceed to attach 2 oxygens, one on the left, one on the right, conveniently drawn here, with the unpaired electron pointing up on one oxygen, the unpaired electron pointing down on the other. And what we discover is that we can conveniently now pair these electrons by erasing the lines, pushing the electrons to the center, and forming a paired carbon dioxide molecule that looks like this shown on this slide. Then we just simply clean that up a little bit, and there we have the Lewis structure for carbon dioxide, and we can check that by counting the electrons around each of the elements. And we do that by drawing these circles around the electrons. And we have 8 electrons on the central atom and 8 electrons on the peripheral elements or atoms as well. And therefore we have a completed octet on carbon dioxide. What about carbon monoxide? Shown here, we've gone through step 1 and step 2 where we've drawn the Lewis dots and we've extended the lines. And now we've proceeded to step 3 where we've attached oxygen to the central atom, carbon, which has the potential to form 4 bonds because of its Lewis dot structure. We then conveniently pair the electrons as shown here by simply erasing the lines because the lines are only there to show us where the potential overlaps are. And when we pair them, it looks like the structure shown here on this slide, but we know that we still have 2 unpaired electrons. So in this case, when we have unpaired electrons that are left over, we never want to leave them left over, so we erase the lines and we regroup these and form what we call lone pairs on the element. In this case, lone pair on the carbon. Next, we count the electrons around each element to determine how well they fit the octet rule. When we do that, we discover that we have 8 electrons around oxygen. However, we're 2 electrons short on carbon. We're insufficient in terms of its electronic balance. Therefore, we will shift 2 electrons from oxygen in the direction of carbon to help fulfill its octet. And when we do that, we discover that we have indeed fulfilled the octet rule of 8 around carbon and the octet rule of 8 around oxygen. They're both satisfied with the electronic balance, and there we have a cleanup version of carbon monoxide. Let's try this with ozone, O3. In this case, we've already drawn the valence electron dots around it, which means in oxygen we have 2 sets of lone pair, and we have 2 unpaired electrons in each of the oxygens, which suggests that our initial pairing or our initial bonding will occur there. Therefore, we've drawn lines to show that, and we've made our initial attachments. We take a look at these attachments. It leaves us with 2 unpaired electrons. In this particular case, we want to regroup. Remember, we never want to leave an electron unpaired in a Lewis structure. So we regroup these simply by sending one of the electrons to the other oxygen. It doesn't matter which direction you go here, as long as you pair them up, regroup them so they're paired, as shown here. And now we will count the electrons to see how well we fit the octet rule. And when we do that, we discover that one of the oxygens is insufficient in terms of its number of electrons. We have 8 electrons around one oxygen, 8 electrons around the other oxygen, but we are short of electrons. We are low in terms of electronic balance on the third oxygen. Therefore, when that's the case, we look for an opportunity to shift a pair of electrons from one of the other elements, in this case, a lone pair from oxygen, in the direction of the insufficient oxygen atom. And when we do that, we have achieved 8 electrons around each of the oxygens to fulfill the octet rule for oxygen, which is located in group 16. We clean that up. We note that the Lewis structure for ozone looks like that's shown here for a bent configuration. What about nitric acid? Case of nitric acid, the central atom would be nitrogen because it has the highest potential for bonding. It has 3 opportunities for bonding, where oxygen in this case only has 2. We note in nitrogen we have 1 lone pair, and oxygen we have lone pairs. So we proceed with the attachment of the oxygens around the nitrogen atom, and it gives us a structure as shown here. And we note we have at least 1, 2, 3 other areas where there are unpaired electrons. So this gives an opportunity to add the hydrogen to one of these sets, leaving us with 2 unpaired electrons. And in that case, when we have unpaired electrons, again, we do not want to leave unpaired electrons in Lewis structures. When that's the case, we regroup. And once we regroup by shifting one of the electrons to the other oxygen, again, it doesn't matter the direction, but we chose to shift it here. And when we do that, that allows us to have lone pairs down the oxygen. Now, since all electrons are paired, we have to count electrons around each element. And when we do that, we discover that we have 8 electrons around the central atom of nitrogen with its lone pair. But when we look at the oxygens, only 2 of the oxygen atoms fulfill the octet rule. We like to also note that hydrogen is satisfied with its 2 electrons. But we have the oxygen with 6 electrons, and when we see that, we use our shift rule, and we shift the electrons from the nitrogen in the direction of the oxygen that is low on electrons. And when we do that, that allows us to now have its 8 electrons to fulfill the octet rule. We clean that up, and we have the structure of nitric acid with nitrogen as a central atom located in group 15 or group 5A. So there you have it, a method of drawing Lewis structures for multiple bonded compounds.